Growing up, my grandma always told me that the land took care of us and it still is taking care of us, and it never asked for anything back.
It is a way of life to always honor the environment. It's not something that you just can turn on and off. It's a living daily lifestyle.
And that acknowledgement is a way to acknowledge that we're coexisting in this land with the native people, and we should acknowledge that this is actually their traditional territory. But at the same time, we are all guests to this land.
The land plays a big factor in who we are. That's what makes us strong. That's what makes us strong people.
And now it is my pleasure to introduce this evening's program moderator, Dr. Raj Bhardwaj. Dr. Raj, please take it away.
Thanks, Maya. Good evening, everybody. Thanks for joining us tonight. I want to thank each and every one of you for taking some time away from a Thursday evening to recognize World Immunology Day. Did you know that it was World Immunology Day today? So tonight we're going to be talking about the immune system and using our immune system to understand, control, and defeat COVID-19. And this is all thanks to people like the Snyder Institute and the Calgary Public Library. They are collaborating and support us in through this pandemic and trying to figure out what's going on. The Snyder Institute is one of the largest research institutes at the University of Calgary's Cummings School of Medicine. Their research is focused on infection, chronic diseases, and Snyder researchers are leading the way in all these areas of research. This research is funded by government, industry, philanthropy, and donations as well. Researchers are exploring everything from COVID-19 to respiratory diseases to the microbiome to cancer treatments, all sorts of other conditions as well. So I want to thank the Snyder Institute members who you're going to be meeting for volunteering to share their knowledge with all of us tonight. And for more information about the Snyder Institute, please visit their website, snyder.ucalgary.ca. You can follow them on Twitter, Facebook page at the Snyder Institute for Chronic Diseases. If you want to know more about upcoming lectures and events, please email Elizabeth Sakibal to provide your information and be added to their list. Elizabeth's going to share her email address in the chat box right away. So another thing, speaking of the chat box, don't put your questions in there. Put your questions in the Q&A box. That's at the bottom of the screen. Anytime during the presentation, we will get to the questions in a few minutes. So tonight, we are really lucky to have with us a panel of expert immunologists and a virologist. So I want to welcome Dr. Jennifer Corcoran, Dr. Chris Modi, and Dr. Nathan Peters. I'm going to ask each of them to actually introduce themselves and to tell us about your area of research. So let's start with Jen. Go ahead.
Hi, everyone. Thank you so much for having me on this panel. Happy to be here. My name is Jennifer Corcoran. I'm an assistant professor in the Department of Microbiology, Immunology, and Infectious Diseases at the University of Calgary and part of the Snyder Institute. And I'm a virologist, so I'm the one virologist on the panel. I'm a virologist by training. And normally my lab is a research lab that studies a virus that causes cancer. But since the pandemic, my lab is also studying SARS-CoV-2, which is the virus that causes COVID, the disease COVID. And we're studying some other human coronaviruses as well.
Thanks, Jen. Let's go to Go ahead, Chris.
Okay, Thanks very much, Raj. My video is cutting out a little bit here, so I don't know whether others are as well. But I'm Chris Modi, and I'm a professor at the University of Calgary, and I'm a lung doctor and also an immunology researcher, and I run a lab within the Snyder Institute for Chronic Disease. And my interest is in how our bodies defend against different types of microbial pathogens. And we study fungi, bacteria, and now also study viruses, namely SARS-CoV-2.
Thanks, Chris. And Nathan.
Thank you, Raj, and thank you to all the participants for joining us this evening. So my name is Nathan Peters. I am a associate professor and the co-director of the Snyder Institute for Chronic Diseases, also a member of the Immunology Research Group here in the Cummings School of Medicine at the University of Calgary. And our lab studies chronic infectious diseases, and we like to try to identify when the immune system gets it right and does a good job against infections, and how to use that information to try and build better vaccines.
Yeah, this is going to be great. With these three experts, we've got lots of opportunities for learning sort of facets about COVID and about our immune responses to COVID. So let's start with sort of a trip through the time machine backwards. I remember sitting in a pub in Calgary watching live D&D because I'm a nerd. And I was watching on stage and also flipping through my phone, and I saw a tweet and I was chilled to the bone. I remember thinking, this is bad. And it was a virologist in Sydney, Australia, who was saying that a lot of doctors in Sydney were calling for a complete curfew, a complete shutdown of Sydney, Australia, because of COVID and the COVID cases they were having. So I want you guys to think back as well to about 13, 14 months ago. Do you remember this situation was going to be a significant problem? And sort of, can you remember your thoughts at the time and sort of, your timeline and all those sorts of things at the time? Should we start with, we'll go in reverse order, start with Nathan.
Sure, yeah, I think there was two things that struck me and really heightened my interest, and were definitely points in time where I thought we might be in trouble here. And the first one was when it was clear that the virus was already quite widespread around the world. And the second point was when it was clear that people were likely transmitting the virus before feeling ill, and that there was this window of transmission that was undetectable. There was going to be people that felt fine, and for a few days they were going to be transmitting to others, and so this virus had sort of hit that sweet spot, and that it was going to be very difficult for us to get it under control.
Chris?
Yeah, so it was certainly a memorable experience in those days in January when we started to learn about this virus, and some of the early literature emerged, and literature published articles were coming out very quickly about that. I suppose the most memorable moment for me was on February the 12th, when the dean called me at home and said, I want you to give a talk on what subsequently was named COVID-19 to the board of directors of the medical school, because they want to try to understand this. And immediately what I did was I went upstairs and made a screenshot of the Hopkins website, and there was just a few cases in China at the time, basically no cases anywhere else in the world. And by the time I gave that talk 2 weeks later, it was all over the world.
Yeah. Jen, do you remember that?
Yeah, I had a similar experience. I think the early reports in January, even as a virologist, I thought this would be a serious epidemic, but not necessarily a pandemic. I thought from the very early reports that it would spread, but it would cause disease in a manner like its related cousin SARS-CoV-1 that caused epidemics in 2003. And it wasn't until about February when it really started to spread worldwide, and we started to realize, like Nathan Peters said, that it was spreading before people were symptomatic, that I thought we're in trouble here. So I was, a little bit late coming to the game, but arrived eventually.
Yeah, it seems that COVID took a lot of people, all of us, by surprise a little bit. I remember being asked in January to speak about it on CBC, and I remember saying, we don't even know if it can go from human to human yet. This is still, animal to human kind of stuff. So let's sit on it and see if it becomes anything. And clearly it became something, and it changed our lives, which leads me to sort of my next question is, can you tell me about not just how COVID has changed your work, because this is now your work, but how has it impacted your life in terms of the pandemic itself? Jen?
That's like everyone, I think all our lives have changed. I think as a researcher, I'm happy to be able to contribute, do research that I think might in some small way help our knowledge about this virus, that maybe we can better fight this virus. But as a person, I think this has been challenging, just like it has for everyone else. And I think as a researcher, I feel lucky that I'm able to contribute in a way that I feel that I can do something. And I realize that makes me lucky. And I'm also feel lucky that I'm able to understand what's going on and communicate that to other people like we're doing tonight. But it has been a challenging year, even for researchers, just like it has been a very challenging year for many, many people.
Mm-hmm. Chris?
Well, Raj, you asked how it affects my life outside of work. And I think what I would point to there is talking to family and friends, how the whole world has changed vis-a-vis immunology, and the fact that people, people that I was close to prior to the pandemic didn't know what an antibody was. They didn't know what serology was. They'd never heard the word RNA before. And now they have absolutely no problem conversing in those various different terminology. They talk about RNA vaccines. They understand how vaccines work, why they have 2 shots. I mean, this is absolutely unprecedented. Just the general knowledge about immunology that the pandemic has provided, and I think that's the most dramatic thing for me, and it's good if because I'm very interested in immunology. Obviously, people used to look at my work and think that it was pretty abstract and pretty ethereal, but now they actually get it, and it's lots of fun to talk to people now.
Yeah, it's fun going from the boring guy at the dinner table to the interesting guy at the dinner table.
That's it.
Yeah. Nathan, how about you?
Yeah, I think I share many of Chris and Jen's sentiments. I suddenly I became very, very popular and was like the go-to person in the family for all things SARS-CoV-2 related. So that was nice. It's always nice when people are interested in your work, especially if sometimes you're doing your best to be a good science communicator and convey the science of immunology and why it's exciting and why it's important. And now suddenly the world's attention is so focused on what vaccines do to your immune system and how your immune system can help you fight off these infections. So that was very invigorating. While at the same time, I suddenly had 3 children and 2 working parents, all gathered around the dining room table trying to do our schoolwork and our jobs. And I guess at the beginning it was kind of a little Swiss Family Robinson and kind of neat. And then very quickly I realized that some of my new coworkers were very disruptive and didn't necessarily respect my personal space. And we had more than a few Zoom calls crashed with a naked 4-year-old running through the background. So it's trying to balance all this. A lot of exciting things, but it has been tough. Very, very thankful that I'm in a position that I can still work. I have the option to work from home if I need to. So very fortunate for that. But it's been a balancing act. Yeah, absolutely.
Yeah, I think it's been a balancing act for all of us. I would like to ask a couple more questions, but I want to remind everybody who's watching, all 216 of you, it looks like, that if you have any questions, just pop them into the Q&A box. The majority of our time is going to be spent taking audience questions, so we're happy to have them. If you see a question that you were going to ask, and if you're scrolling through the Q&A box and see one that you like, give it a little thumbs up and it'll rise to the top, and then we'll know that more than one person is interested in it. That's a lot more efficient than just retyping a similar question. Couple other things. We've had some questions already, and I want to start with one about, because this is an immune system talk, and these, you guys are immune system specialists. Do we have any information, or can you give us any insights into people with autoimmune type problems and the vaccines? Whoever wants to field that, who wants to go first? If nobody goes, I'm gonna voluntold you to go. Okay, Chris, it's up to you for now.
Okay. Yep. Thanks, Raj. So basically what I would say is there are 2 reasons where you should really approach vaccines with caution. And if you have any questions, you should find the healthcare provider, your physician, or whatever healthcare provider you rely on, and seek out their opinion. So ask them an opinion about your specific case. But basically, there are 2 considerations that I use when I talk to patients. And the first is you can have an allergy to these vaccines. So they have a thing in them called PEG, and you can be allergic to PEG. And so if you've had allergies to PEG in the past, that is allergies to other vaccines, then you should be very cautious about that and definitely should speak to your physician. The other issue is in terms of other disorders, so like autoimmune diseases or people that are immunocompromised, basically the general advice is the vaccine is safe. So why would somebody with an autoimmune, why might I tell somebody with an autoimmune disorder not to receive the vaccine? And the answer is, if we're changing their immunosuppressive medications and they're immunosuppressed now, but we can either make them less immunosuppressed, or the plan is to change their medications and they're going to be less immunosuppressed in a few weeks, then what I will do, I'll say, hold off until we get your immune system as good as it can be, and then we'll go ahead. Now, of course, there's many people that are taking medications that suppress their immune system or have cancer. And if those situation isn't going to change, then I encourage them to get the vaccine as quickly as they can.
It's cool. Nathan, Jen, anything to add?
No, I think in this case, I defer to the physician.
Sounds good.
Absolutely.
Yeah.
Since we're talking about immune system stuff again, can anybody give me a rundown or give us a rundown of the idea of long COVID and sort of, what might cause it in terms of an immune system problem? What might cause it in terms of a virus type issue? Nathan, do you want to start?
So I guess, one of the questions that we've had here at the University of Calgary and an area of research that we've received funding to actually look at and study is to look at COVID and this reaction that we have in the lungs as a specific coagulation problem within the lung, the vasculature of the lung. And so this is a question that we've been interested in, and that we actually received a team grant to look at this and study this, both in terms of patients as well as in mouse models moving forward as we launch our CL3 facility.
Cool. And Jen, from a virus point of view, is there anything about coronaviruses in particular that might be sort of making people sick for longer or ending up with a chronic problem? Or is it all viruses have this potential?
So I haven't seen data that would confirm at this point that SARS-CoV-2 is hanging around in a persistent way, in a live virus way in most people. There are examples of immunosuppressed individuals that fail to clear the virus and are infected for many, many months. But I don't think for long COVID in general, we have a clear picture of whether that is a persistent virus infection where there's infectious virus, or whether there's some persistence of viral products like viral genomic RNA hanging around. And then that could continue to elicit an immune response and inflammation that causes some of the symptoms of long COVID. That's a very virology perspective, though, not an immunology one.
That's cool. But it's happened for other viruses before, right? This sort of thing anyway.
Some viruses are well known to establish chronic or persistent infections. That's not a feature that's traditionally been attributed to this viral family, coronaviruses, but other viral families, yes.
Okay, good. All right. Chris, long COVID.
Well, there's a lot to talk about in long COVID. I think if people want to address specific aspects of long COVID, they should put their questions into the chat. There's so many different things to talk about. So really what we're talking about is the syndrome that people call myalgic encephalomyelitis, or chronic fatigue syndrome. And basically many features of long COVID overlap with that. And I would say that, we as the community of practitioners, and I'm sure you see this as well, Roger, learning how to deal with these patients, how best to manage them. Because usually when somebody develops a pneumonia, we're all about getting them going as fast as we can and getting them back to their normal lives. But that approach we've learned is absolutely not the right approach for patients with long COVID or ME. And so consequently, we're learning as we go along. There's some so we're very interested in this problem about how it affects immunity. And recently there's been some talk about whether or not the COVID vaccines can actually help people with long COVID and shorten the duration of illness. And I can tell you that in the couple of people that I've seen with long COVID who got vaccinated, at least after one dose, they didn't notice any difference in their symptoms. But it's early days, and it's only a week or two, and they've had long COVID now for almost a year. So so there's lots that we don't know and lots to learn about that for sure.
Here's another part of long COVID that we don't know, and I'm sure we can learn from you folks. Does it make sense that if somebody has long COVID, that getting a dose of vaccine might actually improve their symptoms? And if so, what's the science behind that? Should we go with Chris because he's the last one to go?
Well, why don't we ask Nathan that question?
Sure.
Because I'm very interested in his answer. So I'm going to learn something here.
Great.
Yeah. So in my lab we study chronic diseases, and we often study chronic parasitic diseases. So infections that maybe hang around in certain people for longer than is typical, or longer than we would expect, and sometimes that has to do with evasion from the immune system, or perhaps the immune system isn't quite making the right type of response. So if you come along with a vaccine and push things a little bit more in the direction that is desirable, then that can push people into a more favorable situation if you're getting to the point where you have clearance. Now there's also a flip side, and that the immune system is very powerful, and sometimes you have to walk this knife edge. You can push it towards clearance, but if you push it too hard, you can get pathology. And certainly in SARS-CoV-2 during acute infection, anyway, sometimes it's the immune systems that's causing the most issues. And so it's maybe it's a little bit case by case basis, but in my mind there may be people where the immune system just needs a little bit of reminding or a little bit of push to get it pointed in the right direction, because you have to remember the virus is trying to do it's working on not being cleared by the immune system or evading the immune system. So in those cases, the little bit of a push from a vaccine could be real positive.
Cool. Jen, anything to add?
Not much to add. I think what Nathan said, I totally agree with. I think if we have a case of virus persisting, and then the immune system just needs a little help to clear all the virus, then vaccines will definitely help that. And they will also help a situation if we have residual viral products. A vaccination strategy would also help clean those up and decrease inflammation to those as well. So I think it's a positive thing in both scenarios.
Cool. Let's maybe segue into vaccines themselves a little bit. We know that there's different technologies of vaccines. There's the mRNA vaccines and there's the viral vector vaccines. Can we get a 2 or 3 minute total blurb on the vaccines and sort of their technology, not necessarily their efficacy and all that stuff, because we've heard about it, and we can go there if people want, but just the technology behind, and what's the difference between an mRNA vaccine and a viral vector vaccine? Who wants to take that? Who wants to take that first?
For sure, that's a question for Jen. She is the expert.
Okay, I'll do my best. So I will start by saying I'm sure many people in the audience have heard the term mRNA a lot lately, but for anybody who's still a little bit unclear on what it means, I heard a really good analogy described recently. So if you're in a restaurant, which of course we don't go to right now, but if you were in a restaurant again, and you had the menu would be the instructions. So the menu is like the DNA. And when the waiter or wait staff is taking your order, they're writing down on a pad of paper what you order. So that's a subset of instructions, and they're taking that to the kitchen. That's like the RNA. And then when the RNA or the order goes into the kitchen and the chef makes your meal that you have ordered, that's the protein or the part of the vaccine that actually does the work to activate your immune response. So in the case of the RNA vaccines, you have the instructions to make a virus as RNA, but not the whole virus, not the whole menu, just one part of the menu to make a virus as an RNA molecule. And those instructions are covered up and protected in lipid, which is basically like a fat blob or a blob of oil, to protect it so it can be delivered into our cells and taken up by our cells. And when the lipid enclosed RNA instructions get into the cells, those instructions tell our cells to make one part of the virus. They tell our cells to make the protein on the outside of the virus, which is called the spike protein. And so when our cells make the spike protein, it is recognized as foreign. It doesn't belong in our body. And we get an immune response to that spike protein. These mRNA vaccines have no possible way of creating a virus. There is absolutely no danger of that at all because they have such a small part of the menu delivered into your body. But they are able to induce really good immune responses because they induce an immune response to the part of the virus, the spike protein that's on the outside. And they induce two types of immune responses, which I'm sure my immunologist colleagues can expand upon. They induce antibody responses. So antibodies are molecules in our blood that can block viruses from infecting more cells. And they induce a cellular immune response. And this type of response makes cells recognize when our cells are infected by a virus and then kill those infected cells. So that's my best explanation of the RNA vaccines. The viral vector vaccines use a virus particle to protect the information that they deliver into cells, but that virus particle, the virus shell, is defective. So instead of using a drop of oil to deliver the instructions to the cell, you're using the outside shell of a virus to deliver the instructions to a cell. It gets into our cell, and those instructions then build the spike protein the same way as in the RNA vaccines, but they cannot build, there are no instructions to build the shell again. So the viral outside shell just falls apart and is destroyed. I think I'll stop there and I can let the immunologists fill in the rest.
That was really good. I'm totally stealing that restaurant menu analogy. I love it. Nathan, Chris, anything to add to that?
No, I think Jen did a great job. You know, we're trying to stimulate these two arms of the immune system, the production of antibody to bind to that spike protein to prevent it from binding our own cells, and then also generating this T cell response, generating these cells that can recognize and kill virally infected cells.
And is there a difference in terms of the technology of the vaccine? So if it's mRNA versus viral vector, does that does that give us a different kind of immune response? Do we know that?
There's a little bit of data on this from the vaccines that are going into people now. And it seems like the mRNA vaccines are more prone to the antibody production, whereas these viral vector vaccines perhaps have a little bit more of the T cell component.
Which then I think brings us to a question that we're getting a lot in the chat is what about mixing and matching different different vaccines. So either within group or outside group. Do we have, I know that there is research ongoing with this, but from at least a basic science or a theoretical point of view, what can we say in terms of the promise of that sort of thing?
Well, I think here, I'll speak first. And I think here, first and foremost, we want to make sure whatever we're doing is safe. So, you want to generate the data to make sure that mixing and matching is a safe thing to do. So that's first and foremost. After that, there is an argument for this type of approach. Maybe it generates a response that has a slightly broader breadth. Maybe it's more stimulatory. These prime boost regimens is a very sort of classical way to vaccinate, and really the data will will tell us which direction we should be moving in. But first and foremost, safety is paramount.
You used a term in there, the prime boost idea. Can you talk a little bit about that and how it fits into the spacing of the doses in the phase 3 trials versus what we're doing in Alberta right now?
Sure. So, the idea of priming and boosting is, when you first prime your immune response, you jack it up this high. And that gives you a certain level of protection. And if you come along with a secondary dose and boost that, then it jacks it up a little bit higher. And typically what happens is when you look at the efficacy of the vaccine between the first and the second administrations, it reaches a certain level, but after that second boost, it's that much higher. And that's why in many of these vaccines, after the first dose, there's something going on. You're getting some protection, but it's really after the second dose where you're seeing those really high numbers of protection. And this just, we're really engaging a natural property of the immune system, which is repeated exposure. The immune system gets better and better at making those matches with the spike protein, as well as the number of cells that are in your body that are specific for the pathogen in question, which obviously here is SARS.
Cool. And then Chris or Jen, in terms of the dose interval in the trials versus in current real life?
Yeah, I guess I would say, so just to add to Nathan's point, and he's made a really good point, and that is when it comes to antibody-mediated immunity, the immune system has a very special property of getting better as it goes along. And the analogy that one might use is it's kind of like a key that goes into a lock. And the first time you pick a key, it might not fit that lock perfectly well, but with time and multiple stimuli, the key gets better and better, and the fit to the lock is even better. And so this boosting phenomenon, as Dr. Peters has said, is better in magnitude, but also the fit is better as well. The molecules, the binding characteristics of those molecules get better and better with time. Okay. I guess my response to your timing of the booster dose is I think that there is a conflict. Okay, and the conflict for me at least arises that when a study is done, whatever therapeutic it is, we try whenever possible to stick to the conditions that were used in that study. So for example, if you have high blood pressure and a high blood pressure medicine is tested, very likely your physician will use the dose and the spacing interval that was studied in that study that showed that it worked. And so on the one hand, as people that prescribing vaccines, we say we really should stick to the study. And so if the study used this booster dose at 28 days, we should be doing it at 28 days. But from an immunological perspective, it becomes more, there's additional factors that go into it. These are theoretical factors and not actually studied. And it's very unlikely that everybody's going to study every condition that they might want to do. But a really good example of this is with the AstraZeneca vaccine. So when it was given initially, it was separated by a few weeks. And then subsequently, a study was done to show that if you look at a booster dose at 6 weeks versus 12 weeks, the response was actually better at 12 weeks than it was at 6 weeks. And that makes sense from an immunological perspective, because sometimes it really helps to get that first immune response going, let it really mature, and then come in with the second booster dose, and you get an enhanced response. And so that's really those two factors together, in addition to vaccine, the pressure to supply vaccines, is what's caused governments all over the globe to say, I think that rather than do the 28 days or whatever the initial study was, let's wait. It's been shown for some vaccines, and it makes immunological sense to work. Is there a downside to it? Yes, there's always a potential downside for everything. And that is that at least a natural immunity we know is not very long-lived for coronaviruses. So is it possible to wait too long? Maybe. We don't know that yet. What is too long? It's certainly going to be longer than we're going to use in this case for the second dose. More than 6 months, more than a year, I don't think anybody knows when, and even whether the vaccine-induced immunity will wane the way natural immunity does. So there's so many unknowns there, but this is I've presented the rationale for why we're waiting longer than those initial studies were done.
And so when you hear about us waiting 4 months, for example, does that worry you, or are you thinking, nah, the science makes sense?
Yeah, I mean, for me personally, I think it's fine. What is the disadvantage of that? Well, the answer is we know that there is good efficacy after the first dose, but there's even better efficacy after the second dose. And so in certain populations, that waiting for that enhanced immunity might be waiting too long. So, and we know that in patients that have received solid organ transplants, so somebody, for example, who's received a lung transplant, the efficacy after the first dose is somewhere around 10 or 15%. So we know that that's pretty lousy. And so that's why the recent decision to make sure that patients that have solid organ transplants, cancer chemotherapy patients, those sorts of things, get that second dose early, because they're not protected really after the first dose, whereas the general population is.
Yeah, I think that's good to hear. I think that there's at least some consternation out there that that we're not following the science, and at least I feel assured that yeah, we are following the science. Maybe not the phase 3 science, but certainly the immunology science and the real world science, the real world evidence. So that's good. That makes me feel better. I'm going to turn this again with regards to vaccines just a little bit more towards the virus. And the variants of concern. And not just about the efficacy of them, but sort of the bigger question of, is COVID going to become the next thing that we'll have to get seasonal or yearly or some interval vaccines for? Because different variants are cropping up all the time. Jen, is that virology for you?
Yeah, you bet. So I think I'll start by saying that viruses always adapt and change and become new variants. That's what viruses do. So coronavirus or SARS-CoV-2 is no different than other viruses. And it does change fairly rapidly, but not as rapidly as some viruses like the common cold virus, rhinovirus, or influenza. It doesn't change as rapidly as influenza. It has, over the past 14 months or so of the pandemic, we've seen the emergence of new dominant variants that we're calling the variants of concern. And largely those have emerged because they're better at transmission or they're more fit, they replicate better, the virus can make more of itself. So the pressure for those to become dominant really had to do with it was better for the virus growth and spread. We haven't yet seen a situation, a real prevalent situation where a lot of people in the world have had either vaccine or infection-induced immunity. So I don't really think we've fully experienced a situation where there's a lot of selective pressure for the virus to evolve to make a variant that is not recognized by our immune system. We haven't had enough people vaccinated for long enough. But I think that selective pressure will be placed on viruses the more we're vaccinated. And so I don't think it unlikely that there will be new variants that continue to emerge. If the variants that we have are any indication, we will have at minimum partial protection against new variants from our vaccines, because that's what we're seeing for most of the variants of concern now, that our vaccines are either completely protective, as good as original SARS-CoV-2, or pretty good at being protective. But I think it's a realistic possibility that we may need to update these vaccines and put the newest variant strains in them and receive boosters each year in future. I don't think that's unlikely.
Okay.
Yeah, and I would say it's important to add when we see the case counts go up, and I'd say probably most people are thinking, wow, there's a lot of virus in the community. From an immunologist or a virologist standpoint, each of those people is a little incubator, potentially cooking up the next variant. And so their immune system is exerting pressure. So instead of just that happening in 100 people, it's happening in 2,000 people, then that's a concern, because we're increasing the likelihood of a new variant. So it's not just about transmission of a stable virus. It's that every individual is a potential incubator, and we don't want these new variants popping up too often.
Yeah, Nathan, thanks for saying that. That is a really important point. The fewer cases we have, the fewer variants we will have, the fewer adaptations we will have. And there's even evidence of immunosuppressed individuals who have failed to clear SARS-CoV-2 and have had the virus for 100+ days. There's evidence of population shifts and variants emerging within one person over the course of the time they've been infected, because after they're treated with something like convalescent plasma from a previously infected individual, that treatment pushes evolution of the virus towards establishing a variant that will evade those antibodies. So we have precedents for this happening, and we don't want it to happen any more than it has to. We want to minimize that.
Cool. There are a gajillion questions about virus or about the vaccines and stuff out there. I think that we can get to some of them in sort of a rapid fire kind of way, but I'm going to hold on to those. I want to ask one other sort of technology question about the mRNA vaccines in particular, because they seem so robust in terms of technology. You can just like put any instructions in there and feed it in, and your body will make an immune response to it. Is this the beginning of a vaccine for cancer?
I think so. I think this is going to be game-changing. I think this vaccine platform will be used for many, many other vaccines in future.
That's really
so
cool. Chris?
I would just add to that, Raj, and say that RNA, the RNA that we have that we use to build the food in the kitchen, as Jen's analogy has it, this is inherently an incredibly unstable molecule. I mean, it stays around for literally seconds. When we try to purify RNA, we have to go to extraordinary lengths to stop it from degrading. And so, and it's a testament to basic scientists who, were not immunologists, but who discovered how to stabilize RNA so that it wasn't degraded so quickly. And that discovery of how to stabilize RNA and get it to persist basically allowed this entire RNA vaccine and other vaccines to emerge and allow us to develop vaccines to, try and save ourselves from COVID-19 and other things as well. And you've already mentioned cancer vaccines, and they're relative. Once you've got that technology, it's relatively easy to manufacture them. To manufacture a vaccine to a variant is just a matter of just changing a couple of the characters that are on that on the order that the waiter takes back to the kitchen. And so this is very important. It's just a testament that you don't know where the discoveries are going to come from in basic science that are going to be catapulted into these kinds of therapeutic approaches.
Nathan, anything?
Yeah, just to echo Chris's comments. What we have here with these vaccine rollouts is the end product, okay, of years, even decades of research. Research done in labs like the ones here at the University of Calgary. And obviously, as a basic scientist, you could see me as being, infinitely biased towards one side of this argument. But, we are not good at predicting where the next big, fundamental, critical idea and discovery is going to come from. It just comes from good, basic science and an investment in basic research and, trying to figure out how the world around us works and how these infections work. And I think the speed with which we've been able to generate this vaccine is unprecedented, but it's not. We didn't just cook it up in a few weeks. This is years of toiling away in research labs, and many of these grants that would have been supported by federal research dollars. You might read the title of that grant and think, why are we studying this? This does not seem like it's ever going to translate to anything, but it does. It does, and this is an example of when
Berger died.
Really,
that was you were involved in that, right?
It's really allowed us to meet a challenge.
The test inquiry.
The Berger inquiry. Why do I know that name so much?
Holly,
That was the first.
your mic is on.
Mackenzie.
Can you turn it off? Yeah, thanks. There you go. All right.
So just, I don't know whether the audience is interested in this, but, Dr. Peters raised some really good points, and it's why publicly funded research in universities works in tandem with corporate money in, the big pharma companies that are, in this case, generating vaccines. They're never going to do this basic fundamental science because their bottom line is driven by their investors. And so they have to turn products over. They do it incredibly efficiently. They do it in a way that's difficult for universities to do. But universities provide all of these pipelines that can then be moved in. And so we work together with industry, universities and industry working together to develop these products.
From an immunity point of view, other than getting vaccinated, is there anything that people can do to improve their immunity, to boost their immunity? I think that we get sort of calls and questions about that all the time. Who wants to take that?
Well, I guess I would say um, if people are truly interested in that question, when to turn up your immunity and turn down your immunity, I would encourage you to read a book. And this is not a book published by an author at the University of Calgary. He's a Pulitzer Prize winner. The book is called The Elegant Defense. And he, in the book, Richtel is his name, points out why that the whole concept of just simply boosting your immunity is not the right thing to do. And very simply put, in a nutshell, okay, if you have too much immunity, and Dr. Peters has talked about this, things get too hot. People generate autoimmune diseases, rheumatoid arthritis, lupus, scleroderma, atopic dermatitis. These are all conditions where the immunity is too hot. People that have immunosuppressive drugs, cancer, solid organ transplants, these is when immunity is too cold. And immunity in most of us is perfectly tuned to be exactly where it should be. And deviating from that leads to the types of diseases that we've seen. So an approach that where we want to turn up immunity assumes that you are so cold, that your immune response is so turned down that you are basically like a cancer patient on chemotherapy, or like a solid organ, or like a transplant patient. And there are a few people that are that are like that.
Cool. I want to sort of delve a little bit to the outskirts of maybe some of the regular sciencey stuff, and talk a little bit about science communication. We've all heard a lot of science, I mean, in this past hour or so, and then we've also heard a lot in everyday media. We're sort of seeing science in real time. Is there something with regards to the communications that you think is being done well? And is there something that you think that we should do a much better job at? And that can be sort of, Alberta or Canada or the world, whatever you pick, dealer's choice. Should we start with Jen?
Wow, that's a tough one. I'm really going to say honestly. I think scientists communicating our knowledge to the public is extremely important, and we should all endeavor to do it as well as we can. I think sometimes in the pandemic we have had examples of fantastic science communication, and as alluded to earlier by Dr. Modi, now people are talking about viruses and RNA and our immune systems in ways that they were not before. And so that's a good thing. But I think there are examples of some misinformation, and there are examples of what I would call yo-yoing communication. One example of that could be, up and down restrictions that we have all faced throughout the pandemic. And maybe some inconsistent messaging around the importance of restrictions. I think I'll stop there and let others comment on their maybe favorite or not favorite examples of science communication. Thanks.
Sure. Who wants to go next? Chris?
Sure. So I guess I would say is, there are some notable examples where media has got it wrong. Okay. But I think the overriding sentiment that I have is, and having done a bit of work with media, is I am, I started off before the pandemic and I didn't do a lot of media work, but have done a bit more lately. I have been really impressed by members of the media. You know, when you see any one of us on the news and it's a, you know, a 15-second snippet, you don't see the entire interview that occurred. And I can tell you that I am really impressed with some of the reporters, the depth of their knowledge, the sophistication of their questions. It's really impressive. And there are a few, and I won't embarrass some of them by naming them or not naming the other ones, but to say these are really outstanding people. They are dedicated to communicating the facts. They do it in an unbiased way, and really at their heart want to inform the public. And so I've really been impressed by that. And I think they do, you know, nobody gets it right every time, but boy, oh boy, they do a pretty good job.
That's great. Yeah. Nathan?
Yeah, I think something that has really come to the forefront during the pandemic is that, you know, this idea that scientists are sort of up in offices and we're all introverts and not interested in interacting with the public or the media. I think this pandemic has definitely taught us that actually this is not true. This is not true at all. And that this opportunity to interact with the public and interact with the media has been really, really fantastic. And it has allowed us to share our knowledge and that, you know, I want to tell people how the immune system works and how SARS-CoV-2 and the immune system sort of engage in this battle, this war, and how we can harness the immune system to help people. So in terms of science communication, have there been some duds? Yeah, for sure. But I think we've reached a level of engagement that I really hope, should we get this under control and get it to a point where it's just something sort of percolating in the background. I hope that this level of engagement can continue as we hopefully take the energy and the focus and the resources that have been poured into this, you know, once we get it under control, shift those to the next big question and you know, keep the conversation going.
Cool. Well, we've got about another 25 minutes to keep the conversation going. I'm going to pivot again to kids and COVID. Two big questions. One is vaccines and kids and COVID. And if you want to talk about sort of safety and when that might happen and things like that. And then the other thing I want to ask about is the contagiousness. Actually, let's get to this first, is, you know, how good are kids at having COVID and at spreading COVID, and why it's been a year, do we really not know? Like, there seems to be a huge divide amongst even the science community about some places saying, no, you know, schools drive infection, and other people are saying, no, community infection drives cases in schools. And then other people saying, well, you know, but it doesn't actually, there's no cross contamination, there's no, or very little school outbreak type stuff. So can we try to pin this down? Because I think a lot of people are confused by this. Nathan.
Okay, well, I'll take the first kick at this, and you know, maybe the audience might not like the answer, because this is a tough one. And I think actually with the emergence of the variants, what we might have thought was true and some pretty solid information in regards to the original virus might be changing with the variants in terms of how much transmission is happening among kids, and how often kids are coming down with more severe infection. So I think that this is in fact a moving target, and you know, there is some data coming out of the northeastern US where there's some, you know, there's new variants circulating where things seem to be showing up in kids a little bit more. Now time will tell. I don't think at this point it's anything to hang your hat on, but I think it's a moving target right now. You know, all I can say is you know, personally, you know, my kids' school here in Calgary, you know, they're all in elementary school, and they've done really well, because you know those elementary school kids have really they do a good job listening about the masks and staying in their pods and all this kind of stuff. So you know, we haven't had too much of a problem, you know, within our school. But you know, that's an N of one. That's just my own personal experience, and we have to remember that it's going to be very different in different communities, and definitely elementary school kids are obviously, as all parents and anybody will tell you, are very, very different than high school kids. Yeah, so that would be my input there.
Okay, Jen.
I agree with Nathan. So I have kids as well, so I have some personal experience with this. And I think the information we have all received is a little bit confusing and somewhat contradictory. I think this is because, number one, the policies are not all the same between provinces, between cities, between school boards. Between schools, you know, the different mitigation strategies that some schools are using maybe are more effective than in other schools. Some schools have smaller class sizes than others. They have more physical space, so they can actually space the kids out more. And I think there even is some inconsistency between school boards, depending on the location, or provinces, about whether or not kids wear masks all the time or they take them off for certain activities. So I think from one scenario to the next, it's just not really comparable data is kind of what I think right now. But I think what is emerging is what Nathan said. Kids can be infected. Kids can get sick. This seems to be worse with the variants of concern. And so we really have to pay attention to whether the mitigation strategies that we are using in School Board A or School Board B are actually enough now with the emergence of the more transmissible variants to prevent the spread between kids. I think what's also become clear is that age matters in this case, and there is a little more transmission between older kids than there is between younger kids. I'm not sure if that's because of behavior or viral load or why that is. I don't think we know.
Okay, good. And then Chris, I'm going to get you to answer this, and I'm going to run and close that curtain because I got sun.
Got too much sun. Yeah. So the question is about children, and I really agree with Nathan's thoughts that, you know, a lot of this is a moving target, and what applied to the traditional strain of SARS-CoV-2 that we saw, you know, the game is changing for sure. And I guess I don't know that I have a lot to add. I know that there's some pretty significant concern amongst the pediatricians who, a group of them wrote a very public letter that was very critical of the you know, current state of restrictions right now. Of course, that's before the restrictions of today, but still, you know, really emphasizing the importance of both disease and transmission in the pediatric population, and urging the government to you know, to have tighter restrictions so that that population could be protected and also protect the rest of us.
Awesome. I noticed a really good question in the chat, which we talked about the prime and boost for the vaccines and how they're all 2 doses so far. How come J&J works with 1 dose? Who wants to take that? Nathan?
This is the Janssen vaccine, and I believe this is the other adenovirus vaccine. Yeah. So, you know, I don't have a good answer for that question. I don't know if Chris or Jennifer a little bit more up on the more recent science behind that.
Yeah, I'll let Jennifer answer that because I don't really know why that vaccine would have an intrinsic property that its effect would be so much more potent after one vaccine.
Yeah, I'm afraid I don't know either. The vector is very similar to AstraZeneca. Like there's so many similarities. So why it's elicited enough protection deemed by the clinical trials they've done after one dose, I can't comment right now.
So then would it make sense though that if you had a second dose like a year later or whatever, that it would boost your immunity that much more? Makes sense?
Makes sense to me.
Okay, all right.
It makes sense, but I think, Raj, you're actually sort of touching on another broader question here, and that is comparing these vaccines.
Mm-hmm.
And this is a big deal. People are talking about what vaccine did you get? Is this one better than that one? These efficacy rates. Well, this only matters if you do head-to-head comparisons of the vaccines in the same population at the same time under the same conditions. And I think this actually speaks a little bit to the science communication issue that we sort of, in the media, these numbers, well, these vaccines give 90% and these vaccines give 60%. These numbers have just gone out, and the natural thing is to compare them and say, well, this vaccine is better than this vaccine. But, in order to sort of make the point to get across the conditions under which these vaccines were tested were very, very different. This is like testing one brand of snowmobile in Brazil in the summer and another brand of snowmobile in Canada in the winter and saying one performed better. And, your conclusion would not be that one brand is better than the other. Your conclusion would be that Brazil in the summer is very different than Canada in the winter. And that's the point to consider. So the efficacy of the Johnson & Johnson after a single shot, in that particular trial, that they hit a number that said, okay, well, you only need one shot. Would two shots be better? Probably. If it was compared against one of the other vaccines back to back, would it show that actually two shots would be better if you test it in this population in South Africa, for example? So it's very, very not scientific to compare these numbers without doing a head-to-head comparison under the same conditions. So just a really important point. All these vaccines are good. And, it's been made for, over and over and over again. But the best vaccine is the one that you can get the soonest. Yeah.
Yeah, and especially with announcement of, over 2,000 cases in Alberta today, I think that's really hitting home, is that there's a lot of COVID out there. And, apart from the worries of allowing, each person is an incubator and allowing the virus to mutate again and stuff. The other thing is that, if you're going out and meeting with a lot of people, there's a good chance you're going to be exposed to it. So, the sooner you can protect yourself with any vaccine, the better. So I think that's another take home from tonight. Can we do a little bit of myth busting really quickly? Just less than a minute for each one of these, and each one of you can have 15 seconds. Do vaccinated people shed, spike, and make other people sick? Because there's that restaurant, or no, there's a store or something in Florida, and they said no vaccinated people allowed in here. Jen,
No, that doesn't happen.
It's not a thing in science.
That's not a thing.
Chris.
Well, I mean, Jen, maybe take 30 seconds and say why it can't happen. Well, you said a minute, Raj. So
Yeah, okay.
You can take my time, Chris. I'm giving it up. I don't even know.
Okay, all right, fine. Okay, next one.
Okay, so that can't happen. Next one. Have the vaccines been rushed? I mean, we know that they started working on them a year ago, and now we've got them. Have they been rushed, and are you concerned about it?
Well, so the way that they were rushed is that normally all the process that to develop and test a vaccine is done sequentially, one after the other, after the other, after the other. And so that's why it takes so long. That's why it takes, a decade to develop a vaccine. And what was done in this circumstance is they were all done basically simultaneously, not exactly, but all done together. And I think that there's a reason why we used to do them sequentially, because you really wanted to know the results and find out how safe it was before you went to the next step. And you wanted to do that both for safety and, if you were a company, also for financial reasons. You wanted to know that it was going to work before you invested all that money. Well, so two things happened. One is the issue of money went out the window. Didn't need to worry about that anymore because there was an urgency. And the second one was we kind of got lucky with the safety issues. We ran it simultaneously. It turned out that they were amazingly safe. And so consequently, we got away with it.
And I would also point out that the mRNA research, like you said, it's been going on for decades. And just to make mRNA stable enough to inject it and then to make it safe enough to inject, that work started in the 1970s. So,
yeah.
All right.
So I guess I would, so I think you raise a good point. There was a good reason to think that they would be safe, and so, and as expected, nothing happened, right? And it's a good thing that nothing happened. Yeah. Right. So we know they're incredibly safe. Yeah.
Cool. Nathan, how do vaccines affect our DNA? Can they rewrite our DNA?
No.
No, why not?
No, these this vaccine is mRNA. The body uses that to make this spike protein. Chris has already alluded to how short-lived it is. We've just managed to keep it together long enough for it to do what we want it to do. And it does not, integrate into our DNA and change our genetic makeup.
Okay. What about the idea that if we're all getting one dose and getting pretty good immunity rather than two doses real quick and getting really good immunity, that could drive the creation of variants? Who wants to take that?
You're generating immune pressure, but again, we go back to this thing. If you reduce the number of incubators, that's great. These vaccines, and where the data is coming out, so it's still early days. But not only do they keep you from dying, not only do they keep you out of the ICU, not only do they keep you out of the hospital, but it seems like they're also doing a very good job of reducing the viral load. So they're reducing the replication. So you're reducing the probability that a variant's going to pop up. So no.
Okay, Jen, I think you wanted to jump in on that as well.
Well, I'll just add, I mean, I think what Nathan said, I 100% agree with. I'll just add that, we do want to make sure everybody gets their second dose in a 2-dose regimen so that their immune response is boosted higher. And so it's more durable, it lasts longer. And initially, I will say that I did do some reading to look into the idea, okay, how long do you get some immunity from the first dose, to try to think for myself what I thought about this extended dosing regimen that we're doing here in Canada. And I was happy to come across some literature on the subject that said that after, in this case, it was testing the Pfizer vaccine, that after the first dose of Pfizer, you do have durable protection for 12 to, I think it was approximately 16 weeks that they looked, which is about the time frame that we are proposing in Canada to have our second dose. So what that means to me is that if you get your second dose a couple months later, you will boost your immune response from your first dose, but you have not waited too long to do so, and your immunity has not gone down too far to allow that sort of spot that we don't want to hit, which is partial neutralization of virus, which may really promote the emergence of new variants. So I guess my message here is make sure you get your second dose. Don't extend the timeline further because you're on vacation. Get it at the 3 to 4 month interval that you're available to get it.
Great. Chris? Anything to add?
Sorry, I was looking at the chat, Raj. So you're gonna have to remind me the question here.
Just the idea of sort of getting, because of the extended dose, could that actually drive the emergence of more variants?
Yes. Okay. So I very much agree with Nathan's thoughts about this. That because of all the good things that it does, we need to do that. And really, it becomes the argument of, should we try to protect everybody 80%, or should we try to protect half that number of people at 90+%? I mean, using just round numbers, and the answer is, if you study that epidemiology, you would come down and say we should protect everybody at 80%, because 80% reduction in viral load, all these different things. I mean, it doesn't exactly translate to that, but that's the concept, at least, is you reduce all of these things by that much. That is going to be enough to halt transmission. And the point about this is, and I feel like I say it every day, this is a race. It's a race of the variant against the vaccine. And right now, the variants are getting out in front, and we need to get people vaccinated so that we can get the vaccines out in front of the variants.
Okay. And then Chris, while I've got you, there's quite a bit going in the Q&A and stuff about your analogy about too hot, too cold with the immune system. And some people are saying, well, wait a minute, if I get vaccinated, how do I know that that's not going to make my immune system too hot?
Yeah. So I guess a couple of points. The first is that we have that level of tolerance, day-to-day variability. And we know that if you get a vaccine, yeah, it boosts your immunity specifically for that. People feel that because their arm is sore, or they get a bit of a fever or feel unwell immediately afterwards. That's evidence that your body is reacting to something. And I can tell you that I was profoundly disappointed when I got my booster dose and didn't feel a darn thing. I was actually looking forward to being sick as an immunologist, because then at least I know that my immune system has seen it. Doesn't mean that I'm not immune. I probably am, but the point is that I was actually looking forward for some evidence. Okay. But I don't know whether the questioners refers to what we went through in the 80s. There was concern in patients that were HIV positive. If you got a vaccine, would that stimulate immunity and actually promote HIV replication? And so there was a lot of talk about that. Okay, but we know that basically that is never going to occur, because it's a very different infection in SARS-CoV-2. We're never going to exacerbate that illness or any other illness. There's no evidence that vaccines that we use, including RNA vaccines, exacerbate autoimmune disease or any other type of illness. So they're perfectly safe to do. If I was a patient in the ICU with COVID-19 and had a really hot immune system from there, and that's why I'm on a ventilator, I probably wouldn't want to take the vaccine then, but I also don't think that anybody's going to give me the vaccine in the ICU either, right? So it doesn't, so a healthy individual, absolutely, we want them to have that immune response, but it won't be hot enough to exacerbate any other type of illness.
Cool. Okay, we could do this all night. And it turns out we have. We've got about 5 minutes or so. I would like to ask you, it's been a hard 14 months. I've lost count. Feels like forever. We've gone through a lot of hardship. We've gone through a lot of loss, a lot of pain. But what gives you hope? What gives you hope for the future? Who wants to take that first?
Well,
Well,
I'll
go ahead, Nate.
sure. So I'll take a run at this one. I think this is a great example of however you want to phrase it, crisis and victory. The scientific community, the worldwide community, our interconnectedness, our dependency upon each other. I think that this crisis has really revealed those very human qualities and our need to support each other, interact with each other, share data, share ideas, to really meet this challenge in a sort of holistic way. And if you want to nerd out for a moment, it's like the unifying power of the alien invasion. It's really great to see scientists around the world and people around the world really understand how interconnected we are, and to internalize that and realize that there's no quick fix locally, because we can't just fix this locally. We have to fix it globally. There's just no other way around it. And the more we work together and interact with each other, the more likely we are to solve the problem. So, I'm hopeful. I'm hopeful because I think it's revealed some very human qualities about science and the human race. So that's pretty positive spin, I think. But you asked, so there you go.
That's a good one. That's a good one, Nathan. Nice. Chris, what brings you hope?
I think, well, one of the things that brings me hope is I don't think we were smart enough to actually design the science around the globe, understanding how nimble scientists could be and how they could take their skills and divert it to a brand new problem that they had never anticipated they would work on. And so somebody who's studying the immunity to fungi, which I study, and never thought of studying a virus, can turn their entire research operation, use their skills, their tools, their equipment, and study a brand new problem. And that has happened all over the world, is scientists have redirected. And you've heard the three of us talk about how we redirected our research to develop, to study a new problem. And it just speaks to how diverse science is in universities all over the world, and how when a problem arises that's of this magnitude, we have all the building blocks in place to study that problem. And so that's really quite an incredible accomplishment, I think.
Cool. And Jen, we started with you. We're going to end with you as well. What gives you hope for the future in these days?
So I think I'll just give you my answer from a few different perspectives. So from the perspective of being a scientist, I echo what others have said. We have responded and come together as scientists to try to deal with this pandemic, and it's been amazing to see. But it really was, a virologist's greatest fear come true, that something like this could actually happen. And what I really hope we've learned from this is that we should be prepared for future pandemics in a better way, and because they may happen again. And so I think we have learned so much from this one that we will be better prepared. Even in Canada, there's now a research group called the Coronavirus Variant Network that I'm part of, funded by CHR, which is designed to help us respond to the variants, but also moving forward to potentially future pandemic concerns. As a citizen, like of Canada and the world, I think Melissa Gates said back in the fall that this pandemic has magnified all the existing inequities that we have in our society. And so I hope as a global society, we learn from it from that perspective too, and we really try to fix some of those inequities. And just from a personal perspective, I think the pandemic has shown me how resilient the human spirit is. And I say that as a person, as a parent, watching my kids go through what is the hardest thing they've had to deal with, watching my grad students work so hard with no breaks and seeing how resilient they can be, thinking about like the frontline workers, the healthcare workers, and how hard they've had to work to keep people alive that get COVID. So it's been amazing to see the human spirit is so resilient. And so that's, I think, the hopeful note that I will end on.
Thank you. Those are very wise words. And I want to thank all of our panelists, Jen and Chris and Nathan, for volunteering your time tonight. Thank you to Maya with the Calgary Public Library, for Elizabeth and Holly as well with the Snyder Institute. And thanks to everybody who hung in there and put their questions in and listened and watched and thought and engaged in our conversation today. If you want to be added to the Snyder Institute community contact list and be informed about other lectures and events, email Elizabeth, who's going to put her email address in the chat. If you're interested in helping us to move our research from basic science to the real world, then please consider participating in studies and investing in research through donations as well. If you want to get more information on all of that, snyder.ucalgary.ca/donate if you want to go to the donate one. And now I'm going to hand it back over to Maya with Calgary Public Library for her closing remarks. Thank you, everybody, for being here.
Thank you.
Maya,
Maya, you're muted.
And thank you very much. That's the most popular phrase in this and past year. Thank you very much. So I'd like to thank our panelists and the moderator from the Snyder Institute for Chronic Diseases for their presentation and an engaging discussion. And thanks everyone for joining us this evening. If you enjoyed this program, we'd like to invite you to sign up for a similar program, but with a different topic. It's coming up on May 3rd. It's a mini medical school program series. It's on the library website up for a sign up. So please go to the Calgary Public Library website and sign up for that one. Also, the book that Dr. Modi has mentioned today during the discussion is available on the Calgary Public Library website. So please feel free to download it as an ebook or check it out and pick it up. And with this, I would like to say thank you very much again, everyone. Stay safe, stay healthy, and I'll see you around maybe next month. Goodbye, everyone.